He's a king of trolling.
Today we're going to talk about
I read his book.
composite functions. Alright, so the thing is, what we've been doing is combining functions. When we talk about combining functions, we're using our operations of addition, subtraction, multiplication, division. Today, when we do a composition of functions, all we are doing is substitution. Okay? Bless you. Don't do it again.
Office now.
Hallway.
All we're doing is substitution, and I don't really want to talk too much today about how to find domains of these things. I just want to get you kind of versed in the skill of substituting and evaluating, and also in kind of reading the notation and pulling it apart and understanding what the notation means. Tomorrow, we'll kind of talk about the domains of these things and how we can decide them and determine them. It's a little bit more difficult than dealing with domains of combined functions. But a composition of functions, okay? All we're going to do is we're start with two functions, whatever they might want to call them, f of x, g of x, h of x, whatever they want to call them, and really whatever they want their expression to be, okay? We're going to start with two general functions, okay? So let's say that we have, what do we say, f of x over there is x squared, or is it radical x? Radical x. And then g of x, they say, is x squared plus 1. Is that right? Alright. So x squared plus 1. So we look at those two functions. And what they're going to ask you to do is basically, can you take one of these functions and let one of those functions be your input value for the other? Okay? So I can take radical x, okay, and input that as that x value right there, square it, add 1, so forth. Or can you take this one and put it there, okay, evaluate and see what your new function looks like, okay? And we can do this with two functions, we can do it with 3 functions, we can do it with 4 functions, however many we need. But I think maybe the first thing we should do is talk about kind of what we're doing numerically. And we see up there what we get, what our new function h of x will look like. But let's think about this. Let's say I gave you some notation that said f of g of x. Okay? And what that means is the way we're going to look at that, we're going to look at the innermost function. The innermost function is going to be the one that has the variable attached to it. So g, in this case, is the innermost function. So we're going to look at that. Okay? And I'm going to change the x value to something numerical in here in a minute. But what they're saying is that you're going to take whatever you get, whatever your output value, because this is an initial input, this x is an initial input. You run it through g, and you'll get an output, right? Does that make sense? Well, that output then, you want to use it as an input for f. Alright? So, when I write this, so I'm going to say, I'm going to change that x right now to, let's just do one that's, that doesn't matter. Let's go 3. Okay, so I go f of g of 3. So I work on the innermost function first. So I'm going to evaluate what g of 3 is. Well, I'm going to come up here, put 3 in for g. And it's going to spit back 10 to me, right? Okay, so with an input of 3, g of 3 is now equal to 10. So instead of writing this as f of g of 3, can I rewrite it as f of 10? That kind of makes sense? So I use an initial input of 3, run it through one of the functions, get an output. Okay? That output now becomes the input for the remaining function. So now I'm going to take this 10, I'm going to run it through that, and I should get radical 10 back, right? So the idea then is that f of g of 3 was radical 10. And we should be able to do that then for any value that's ultimately in the domain of g. Okay? If I, try 4, okay, so plug 4 in here. Okay, I'm going to go up here wherever I see dx. It's now going to become 4. So now I get 16 plus 1 is 17. Now I'm going to come down here where I saw f of g of 4. G of 4 is now substituted in with 17. It's equal quantity. And now I'll substitute that 17 into this function f. And we get radical 17. Is that pretty easy?
Yeah.
Okay. So now where it gets a little bit more difficult is when we don't know what x is, but we still want to come up with f of g of x. Okay? So really all we do, but it's the same concept. If you understood that substitution, hopefully you understand this substitution. Remember, g of x was the rule that gave me that 10 or that 17, right? Okay? So if I don't know an input value, an initial input value, this function is going to become my input value. So I'm going to actually rewrite this as f of, now g of x was x squared plus 1, right? So I'm going to write it that way. Okay? Where that x squared plus 1 before was the 10 or the 17 that we dealt with, right? We just don't know what x is, so we don't know specifically, is it 10, is it 17, is it 26 or something like that. Okay? So now, the way I read this is to go to the f function, and wherever you see x, wherever you see your input value, your input position, you're going to replace it with what? That. Yeah. I'm going to go to this function here, and wherever I see x, I'm going to replace it with that input. So x becomes x squared plus 1. I keep that square root there. Okay. The way I kind of visualize, we talked about this in the last class, the way I visualize it, the x is kind of a, in the substitution kind of technique or format here when we get to this last step, this x is kind of like a placeholder. Okay. If you guys remember back to like an Algebra 1 or 8th grade math, and they're trying to get you to learn how to substitute, they would put kind of like a box there, wouldn't they? Alright, well this is what is going into that box. Everything else stays static. It stays the same. The square root doesn't change. If I've got a plus or subtraction or multiplication or division of anything else that is non-variable, it all stays the same. Okay? So the hope is that you realize that this function here, this f of g of x function, still has the same kind of format this one did. It's still a square root, right? It's just that my input now is a little bit different. Okay? But here's the lie. So this is the new rule, f of g of x. So here's the question. And then here's the necessity and the usefulness, I guess, of this new rule. Is because now if I ask you what f of g of 4 is, okay, you now know that this was f of g of x, right? So your x now became a 4 here. So what's x squared? It'd be 4 squared or 16, right? Does that give me that radical 17 we found earlier? Okay. If I do f of g of 3, okay, well that's, 3 squared would be 9 plus 1 gives me that radical 10 again. Okay. A lot of times though they don't like to, because writing f of g of 4 and f of g of 3 is kind of a pain in the butt. They'll say once you create this composite function f of g of x, rename it as h of x or some new function, whatever variable, whatever letter you want to use. And then this would be then h of 4, and this would be h of 3. But the rule, creating that rule analytically with the algebra here, okay, this x squared plus 1 underneath the square root, allows us to evaluate this thing at many, many points, okay, infinite points, which is nice, because if I just, if I, on a test or a quiz, say, okay, find f of g of 3, and that's the only thing I asked you to do, my hopes are is that you guys take the 3, plug it in this function, get a 10 back, take that 10, plug in that function, get your answer, right? Okay, that's very simple, very quick to do. But if I ask you this, stuff like that. Are we going to want to take 3, plug it in there, get 10, plug it in here, get radical 10? Take 4, plug in there, get 16. Plug in here, get radical 17. Or sorry, get 17 here, radical 17 here. And then do that with all those values. Now it's a pain in the butt. So what we can do, real quick, is develop this rule for f of g. Okay? And now that I have that rule, I could either substitute those values 3, 4, 5, 6, negative 6, negative 8 in here using my, doing it by hand and using my arithmetic that way. But couldn't I also kind of do this? Can we go to our calculator? Oh, that was the quiz I was going to give you today. You're welcome. Ooh. Ooh. Yeah, that's me swimming. Those are my real feet.
What size shoe do you wear?
That's a good form.
Thanks. Alright, so once we create that new rule, we can just go to y equals, and can we type that rule in? Go to square root x squared plus 1. Okay, make sure I put it all in parentheses so that everything gets underneath that square root. But now if they want me to evaluate at all those points, I'm going to go to my table. I'm actually going to adjust my table. Just go to ask. Go to my table, and now I'm going to find, okay, so this y3 is f of g of x. So I'm just going to start plugging in the values that they asked me for. So they wanted 3. So we see we get the, that's radical 10, okay? So maybe with this, because we have the square root, it's going to provide a rational number. Maybe this isn't, if I wanted exact answers, maybe this isn't the route to go. But we can do 4, we can do 5, we can do 6, we can do 7, okay? And we get those results real quick, right? Okay? If, like I said, if the function wasn't creating irrational numbers, and we would be able to get maybe whole numbers back, that might be a little bit more useful. This is the graph of that function, okay? And if we compare that graph to the original functions, okay? The original function, let's say f of x was square root of x, okay? And then g of x was equal to x squared plus 1. Okay, here's what's happening here. Okay, we are taking x values as an input. Okay, so I take maybe x value of 0, and I run it through the blue curve, right? The blue function, and it's going to give me back a 1, correct? So an initial input of 0 gives back a 1. Okay, now I'm going to take that 1, and I'm going to run it through this curve here. Okay. Well, when I run through that curve there, okay, what's the square root of 1? 1. Okay? So now, think about that value. We started with an initial point of 0, initial coordinate of 0. You ran it through two functions, got an output of 1, right? So when I do the composite function here, f of g of x, I should have the point 0, 1 on that curve, right? Okay? If I do, let's just do... if we did that 3, okay, so 3, plug that in first, and it spits back the 10 that you get right there, correct? You take that 10, all right, and you run it through this function, you get radical 10, correct? If I plug in radical 10, and we go back to radical 10 on this was, I think it was like 3 point something, 3.16, okay, well look at 3, look at the orange curve, okay? That value right there is pretty close to 3.16. Does that make sense? Okay. So that's how we're getting these points to graph that composite function. Okay. We'll talk about how the domains of these things impact the orange curve tomorrow. Okay. That's the first composite function. Now, we can do the same thing and create a rule for we got f of g of x. Let's do it this way. Let's find g of f of x. Okay, develop that rule. All all we did is we flipped the f and the g, right? So now we're flipping the input the initial input function. So this is the innermost function, so I'm going to focus on that. Okay. And if you want to, if we want to go through this, we can do the same idea as what we did before. If I say g of f of 3 now, okay, take that 3, now you're going to plug it into f. So I get square root of 3, right? Okay. Well, if I plug square root of 3 in, come over here, okay, square root of 3 squared is 3 plus 1 should give you 4, right? Where before, if we had f of g of 3, that was giving back radical 10, right? What are we seeing about when we flip the f and the g, when we flip those functions? We do kind of the, I don't want to say opposite, I don't want to say inverse either. When we just transpose the composition, do we get equal outputs? No. Okay. And in general, you don't. You won't. Okay. But sometimes we might. Okay. And sometimes it's really nice when we do. Okay. So the idea then is looking at this as a rule. Okay. Take my f of x function. I'm going to replace it right there. So it becomes g, but f of x is now square root of x, right? Okay. Now I'm going to take that square root function, that input, and it's going to become the input for that right there. Everything else is static. Everything else stays the same. So that's why I kind of like to think about that as being a box. Okay. I'm going to put inside that box. Right now inside that box is x. But when I substitute, it's going to be square root of x inside that box. Does that make sense? The 2, power 2, the plus 1 is static. It does not change. So I'm going to plug in square root of x. Okay, my box kind of visually is a set of parentheses maybe. We'll square that. And then add 1 to it. Okay. Well, that result gives me x plus 1, right? Okay. Now, the idea, tomorrow, let's say that I choose, like let's say we'll take negative 3 here for x. Okay, or negative 2 or negative 1. Anything that's negative. Okay, do you get an output? Because remember what we're doing here. This plane is the real numbers. Okay, there are no complex imaginary numbers up there, right? So if I plug in x to be negative, let's say we, just looking at this, they say x to be negative 3. Okay, if I plug negative 3 in, okay, to this function, I get, let's do this, let's go negative 4, make it easier. If I plug negative 4 in, I get 2i back, right? 2i is not a real value to input there. Does that make sense? Okay. So when I graph this stuff, when I graph this final function, g of f of x, so what this one here is g of f of x. When I graph that, we shouldn't see x values that are negative because they don't provide that initial input value that we're going to run through our second function. Does that make sense? Okay. And if we graph that, so g of f of x, we get, that green curve, or green line. Okay, it's a terrible color. It looks pretty good on my computer. Let's see here. That better? All right. So we get that yellow line. Okay, still looks a lot better on my computer. But you notice that yellow line, if I get rid of the other ones, that is a portion of x plus 1. Okay, right? Does that make sense? But because the initial function f of x was not allowing these negative values to exist, okay, we can't graph the composite over here. And maybe another way of thinking about it is, remember we're taking values off of that curve there. Values off of that curve. So an x value of 2, let's go x value of 4. X value of 4 gets a y value of 2 back, right? Well, that y value of 2 that you just got back now becomes the point, or the input value for that function. So you take that 2 and you run it through here and you get 5, right? That's why right here at 4, the original value was 4, Put that into the red function, you get 2 back, right? That 2 gets plugged into the blue one and gets you 5 back, right? So the original value of 4 changed into the value of 5. If we look right there, is that value 5? Yeah, okay. So on that final function, we get the 0.4, 5. Well, over here, if I try -2, there is no input value that I can choose to get an output for that red curve, right? Okay, so then if there's no input there, there's no output, and then there's no input again for the blue one to get an output for the yellow one, okay? I know that's a lot of input, output kind of verbiage, but there's really no way around saying that. Tomorrow we'll talk about how we can kind of algebraically determine that domain, maybe without looking at the picture. But you see then the question that they often ask. One of those is, the orange one there is f of g of x, which we said was that function. And the yellow one is x plus 1, which is that function. And the question is, are those equal? And the answer is no. Okay, so composite functions are not always commutable. Okay, think about this though. Let's go. I got to do a little bit of a. Well, you should be able to do it this way. Let's go. Let's go. F of x is equal to x. So don't write this down. Just watch. F of x is equal to x cubed. So I get that, and then I say g of x is equal to square root, or sorry, cube root. So the way I have to write this, I have to write it as x to the 1/3. To do cube root on this. You don't want me to change the way it looks. So I get those two functions, right? So cube root looks like that. Or sorry, power of 3 looks like that. Cube looks like that, and that's the cube root. Okay. Well, if I do this, if I go f of g of x, I get that line right there. Okay, so that's f of g of x. That makes sense? Okay. Now I'm going to do g of f of x. And what happens is I get the exact same line, don't I? Okay. So, in that situation, those two things are commutable. We find out that, we're going to highlight it, where it says h of x there is f of g of x. And here it says p of x is g of f of x. We get the same result. Basically, we get x back, right? When that happens, you have a special scenario, special case in regards to these two functions. And that's what the next section's about. But those two functions, because they provide the same rule when I compose them, are referred to as inverses of one another. Okay? And you guys know what inverse, adding, subtracting are inverses, right? Inverse operations, they undo each other. Multiplication, division, square root and powers of 2, logarithms and exponentials. Here we've got a cubic and a cube root. They should undo each other, right? And the idea of what I mean by undo each other, and I'll talk about this in a lot more detail later, but let's say I've got f of x is equal to the cube root of x, and g of x is equal to x cubed. Let's say that we find, let's go f of g of x, right that way. If I plug in 3 here, okay, plug in 3 to here, you get 27, right? 3 to the 3rd is 27, so I get f of 27, okay? Well, when I plug 27 in here, the cube root of 27 is 3, right? So I started with an input, it changed to 27, but the other function took that 27 and got me back to the same original input that I started with, right? So my first input becomes identical to my last output, and when that happens, these functions are referred to as inverses. They undo each other, okay? No matter what number you start with, if I start with pi, running through here, okay, and then take that quantity, pi cubed, and run it through here, I get back to pi, no matter what number I start with, okay? And the same thing happens kind of in the reverse order. If I take g of f of x, but let x now be, let's do an easy one, let's go 8. Okay, if I put 8 in there, what do you get? 2. So now I'm looking at g of 2. Plug 2 in there, what do you get? You get back to 8, right? So that's why we're seeing the line y equals x there, is because whatever x is, as an initial input, you get x back as your output, right? And input comma output is an ordered pair, so 8 comma 8. So that's some stuff to kind of see where this section is going to take us. And then, again, going back through everything that we're going to talk about in this course, we're going to start talking about new functions in chapters 3 and 4 and 5 and 6. And in each one of those, we're going to have a new function. Say we talk about logarithms. The next thing we'll talk about is exponentials, and we'll talk about how they relate to one another as inverses. We'll talk about trigonometric functions, sine, cosine, and tangent, and then we'll talk about these things: tan inverse, sine inverse, cosine inverse. You guys want to talk about those in geometry and algebra 2? Okay. Well, those are functions like f of x and g of x that undo each other. Okay, so the tangent inverse and tangent go together, sine and sine inverse, cosine and cosine inverse, and they undo each other. Okay, you've used those a lot in the past, but the logic and the reason why they work is what we're working on right now, these composite functions. Okay, some notation stuff that is important for composite functions. Different ways you're going to see it. We've been saying like f of g of x. That's how I read that. F of g of x. Okay, perfectly fine to read it that way. Some textbooks refer to it as, we'll read this, they'll say f composed of g of x. Okay? And a lot of times you're going to see a notation like this. F, and then there's going to be an open dot, and then a g, and then our x. Okay? And we read that, we can still read that f of g of x, but usually that dot is referred to as the word composed. Okay? So f composed g of x. Okay? Or sometimes you'll see it f composed with g of x. That's a notation that we're going to have to get used to. Just being able to recognize it, because I never use that notation. Whenever they write in like a web assignment or a homework assignment, whatever, they write this, or even on a test, because you're going to see this written on the test. I always look at this and then transfer it back to this. And it's really easy to transfer it back to this. Basically, all you have to do, there's a couple different things you can do. I can take that composite out and just put parentheses like that. Does that kind of make sense? And that gives me exactly what I want. Last class, we kind of talked about it this way. They are in order. Okay, so I start with the F left to right, and I put a parenthesis, and then I go to the next letter, put a G, okay, and then once I start recognizing parentheses up here, I just continue to put those parentheses in and keep writing the information. Now, what happens is once you get that parenthesis, you still have this one open, right? So you got to close it. We also talked, maybe you do it this way, okay, because this ends up being the innermost function. Whatever letter has the x stuck to it is the innermost function. So we can do it this way. Say, start with the g of x. Say that's my innermost function. So there should be things to the left of that, outside of it. So if that's the innermost, write that down like that, and then move my way out, and I write f. Okay? And really what happens is, and why that's important, is because we can do this. I can ask you what f composed of g, composed of h, composed of w of x looks like. We're going to have 4 functions, and we're going to take basically this x value, run it through w, get an output. Take that output, run it through h, get an output. Take that output, run it through g, get an output. Take that output, run it through f. Does that kind of make sense? You can do this as many times as you want. You can compose as many functions as you need. So the easy thing to do, again, you can do it this way. You can say, okay, that is going to become a parenthesis. Just close it off. That is going to become a parenthesis. Close it off. That is going to become a parenthesis. Close it off. And now you can see that is the innermost function. And you start working your way from the inside out. Does that kind of make sense? People struggle, for some reason, people struggle with this notation. All right. I'm one of those people. When I first started seeing this stuff, when I was your age, that F composed G thing kind of threw me off. Once I learned that, man, this makes sense, I can do it this way, that was easier to think of. So let's do one of those that is, multiple functions instead of just 2 and 3. This is really the idea, though, kind of visually. We've talked about functions as machines, or if I take an input, run it through a machine, okay, get an output, take that output, run it through another machine, I should get my final product, right? The idea, of machines. Let's say we take. I don't want to say that. I'm trying to think of take a machine, like a food processor, run an apple through it, you get applesauce, right? What's another machine I can run that applesauce through to get something back?
You can use applesauce to make like apple cake, like an apple.
Okay, so I take that applesauce and I put it in my oven, and now I got apple cake or something like that, or really hot applesauce.
Well, essentially,
but it's a different output, right?
Essentially, you mix it with like bread.
Yeah. But the idea, when we talk about inverses tomorrow, the idea of inverses is, or later, probably Monday, is the idea of inverses is I take an apple, run it through my machine, my first machine, get applesauce, right? Then I would have another machine, put that applesauce in it, and what would come out? An apple. Because we start, they undo each other, right? You have two, if they're inverses, they're two machines that undo each other. So you start with an apple, run it through, get applesauce, pour that applesauce into another machine, and it puts it back together as an apple. Okay? That doesn't work that way, right? In the real world, it doesn't work that way. That's the way functions work. Okay?
Time to contact the science department. Mr. Grimm, I have a question.
I mean, that's what they're going to do with people when they start transferring through space, right? Like through wormholes and stuff.
Sodium chloride.
Huh? Right? They're going to take your body and dissolve it and send it through space real fast, and then when you get to where you want to go, they're going to put it back together?
Light speed.
Yeah.
I love it. Let's figure it out.
Alright, so f of x equals x squared. And g of x is equal to x minus 3, right? So this is a little bit of an easier one. Then we'll do the one with the 3 functions. If we want to find f composite g of x, again, I'm going to rewrite that as f of g of x. Okay. I'm going to rewrite. I'm going to take the g of x and replace it with what?
X minus 3.
X minus 3. So whenever you're doing the substitution, remember substituting. Back to 8th grade, 7th grade math, when you substitute, only the thing that you're substituting changes, right? So I'm only substituting g of x, so f does not change. This cannot go to something different, can't disappear. And now I read that remark, and what am I left with? I'm now left with f of x minus 3. So now I go to f, and wherever I look at my input object in f, which in this case is just that x, I'm going to replace it with what? X minus 3. So now it's a quantity that I'm putting in here. So whenever you're substituting a quantity, make sure you put it in parentheses. Okay? Because if I don't put it in parentheses, understand what that means? That means x squared minus 6x plus 9, right? If I don't put it in parentheses, it just means x minus 9, right? Okay? That means a line. This is a parabola. The parabola is what we want. Okay? If I do g composite f of x, okay, again, that's g of f of x. So now f of x is what? X squared. Okay, so that thing right there, I replace with x squared. Now I'm going to take that, and I'm going to go to g, and wherever I see x in g, I'm going to replace it with what?
X squared.
X squared. So now I've got x squared. Okay, now, because there's a monomial, I really don't worry too much about the parentheses, but if you want to put parentheses around that, that's fine, but it doesn't really change anything, right? So we got x squared, and then my minus 3 has to stay there, right? Okay? Everything that is, additional adding, subtracting, multiplying, dividing, powers, roots, that are not part of what you're substituting, they need to stay. Okay, they keep saying static. That means that they're not moving, right? They have to stay put. Now the idea is, how do these things differ? Are these things the same? Is that function there the same as that function there? No. What's the parent function that goes with this one? What is the most kind of elementary type function that you would start with if you wanted to graph this? X squared, right? And this minus 3 to the x does what to the x squared? Moves it to the right 3 units. So what this would look like is that parabola, right? Okay. If we look at this, what's the elementary fundamental parent function that you start with here? X squared again. But what's that minus 3 do? Moves it down 3. So we do get two different rules, right? Okay, because the graphs that are developed from them are different. Let's do one more, and we'll stop. Is that camera still on?
Yeah, it is.
Fantastic. Yesterday I was only running for like 3 minutes and then it shut off.
It has a red battery.
It does have a red battery?
It does.
Oh, it's going to shut off soon. Alright, so we can start doing composite functions of 3, 4, 5, 6, however many functions you want. So let's do, we've got f of x will be equal to something, g of x will be equal to something, and h of x will be equal to something. And if we go to the next slide, we've got f to be x over x plus 1. We got g to be x to the 10th, and h is x plus 3. Okay. So now I'm going to rewrite. I'm going to find f, composite g, composite h of x. Okay, and see what that is equal to. Now, what happens is, in the last ones we had two functions. They asked you, can you take f of g and then flip it and find g of f and ask the argument, are they the same, right? They're not going to do that with these because there's actually 6 different ways that we could write these 3 functions. Composite one, does that make sense? I go f of g of h, I go f of h of g, I go I go g of f of h, I go g of h of f, and I keep going through and find there's 6 total. Okay. If I let the functions repeat, because you could do that. Okay. There's actually a total of 27 different combinations, it's permutations of different rules that you could create. Okay. So they're talking about that. The reason I talk about it is that they're not going to ask you, is this equal to h of f of g, because they're not going to be. I like to rewrite this as f of g of h of x. Okay, and I always highlight, whether I do it physically or visually, I highlight that innermost function. It's going to be a practice you want to get used to, not just for what we're doing now, but when you get calculus, they're going to talk about innermost functions a lot, and we're looking inside the kind of, they're called nested parentheses when we look at the innermost. Okay, and we start doing our work there. So now, this first one is just a direct substitution. What is h of x? X plus 3. So this thing's going to stay the same. F, g, but now I make the direct substitution that h of x is x plus 3. Okay. Now I go to, it's cleaned up a little bit, right? Okay. Now I've got rid of the h. Now I go f of g of x plus 3. So I'm going to go to g, and wherever I see the x, I'm going to replace it with what? X plus 3. So this is going to rewrite as f. Okay. And then x plus 3, because it's a binomial, so I need to put parentheses around it, raised to the 10th power. Does that kind of make sense to everybody? Now, you're going to come over here, and you're going to replace that x plus 3 raised to the 10th power, and for x in this one. How many places you got to input x?
2 places.
2. So that is going to become an x plus 3 raised to the 10th, and so is that. And that is going to provide us then, finally, x plus 3 to the 10th, all over, x plus 3 to the 10th, plus 1. And that then becomes f of g of h of x. Is that thing there? And we would probably maybe rename that as maybe, I don't know, some new function. Easier to talk about if I just call it m of that new function, m of x or r of x or whatever. That's usually what they'll do. Is that something we can do? Do you recognize that that's just substitution? All right. In the past, and this is what I kind of talk about it this way. In the past, we've gone over this, going to maybe assuming that we have done this before or seen this before. Have you seen this before? Okay, somebody saying yes, Chris saying yes, somebody saying no. My hopes are that we get very proficient at this because it becomes a very, very useful procedure throughout the rest of mathematics.
On a test or a quiz, would it be wrong if we were to simplify that that function?
The x plus 3 to 10?
Yes.
You can, but you remember this thing over here? This is how you'd have to expand that x, because x plus 3 to 10th means x plus 3 times x plus 3 times x plus 3 10 times. You guys remember what this thing's called?
The Pascal's triangle.
Yeah, it's Pascal's triangle. And basically you'd have to go down to, so this is something squared, right? This is cubed, this is a fourth. You have to go 5th, 6th, 7th, 8th, 9th, 10th to get that to expand. So no, don't expand it. If at any state, if it was maybe squared or cubed, there might be a need to expand because you might be able to condense and combine like terms, stuff like that. But in general, no, don't worry about it.
So,
Go ahead.
so on a homework assignment, even if it was like that, you would still have it corrected.
Yeah, they're gonna accept that. Yeah.
Okay.
See you tomorrow.
Oh, Faye, it hasn't died yet.
Good.
And there's literally nothing in the little battery thing.
It's gonna beep here in a minute. Probably die when I